In the meantime, keep on grinding through harmonic oscillator. I think we probably will only talk about this maybe one more lecture after today. But we'll see. I really want to get into molecules. I didn't really spend a lot of time on molecules in the last year, and I think we should spend more time on it. We'll talk more about molecular orbitals, wave functions for molecules, and how to calculate them. I'll even introduce you, if you haven't taken computational chemistry yet, I'll try to give you, hopefully in this month, a little demonstration about how we calculate molecular structure, right? How do we use quantum mechanics to calculate things about chemistry, right? So I'll give you a little history lesson about it, like I always do. We'll do some I'll do some calculations and demonstrate them for you in class. Talk about how we set calculations up, what are the strategies that we want to do, what are the approximations that we have to make, and what kind of results can we get out of calculations. So I want to set up our theory for it, and I want to understand how a molecule functions in terms of as an object that we can manipulate mathematically or physically. And we're not quite there yet, but we will get there, and we'll be able to come up with some ideas about how the wave functions of molecules, how electrons are organized inside of molecules. We'll be able to calculate them and actually look at not experimental results, but true theory. We'll be able to solve the Schrodinger equation for any molecule, basically. I'll talk about how we do that. And we'll realize that we can't really do it on the board, but we can write a computer program to do it for us. So I'll talk a little bit about computational chemistry just briefly this month as well, before we dive into spectroscopy at the end. Okay, so where were we? So the idea is that we're treating our molecule, our diatomic molecule. Again, I like HCl, but let's just keep it general. We have a molecule AB with masses Ma, masses Mb. If we just leave the molecule float freely, not doing anything, we're not stretching the bond or anything like that, we assign what we call an equilibrium bond length. I called that L0 last class, which is the length of our spring. Typically, chemists use the term R sub E for the equilibrium bond length, where the E stands for equilibrium. Right, and that is the bond length that is associated with the minimum of the potential. Right, so right smack in the potential is right at the bottom. The minimum of the potential is some bond length, and that's what's called the equilibrium bond length. What we're going to learn, and hopefully we'll do it today, is that the true bond length of a molecule is very rarely equal to R sub E. Right? If the bond were perfectly harmonic, right, that the potential of the bond, energy of the bond, is 1/2 kx squared, like a perfect spring, perfect oscillator, R sub E would be the bond length, right? It's right in the middle. And we'll show that the average bond length of each wave function, each state of the molecule, V0, V1, V2, all of them, the average bond length is R sub E. On average, the bond length is R sub E. But we don't actually, in experiment, we don't, in reality, harmonic oscillator isn't a correct approximation. Right? Molecules aren't perfectly harmonic, which leads to a bond length that's slightly different than R sub E. And I'll introduce that concept today. But first I want to finish up with harmonic oscillators, and then we'll talk about what is not a harmonic oscillator. And I just want to point out a couple of really interesting things about harmonic oscillators. One is that, well, just like everything else, the functions are orthogonal. So harmonic oscillator wave functions are orthogonal. Of course, every system we've ever looked at have orthogonal wave functions, but the integral of psi v prime, psi v, is equal to 1, or has two results. I'll add dx here. Either 1 if v prime is equal to v, or 0 if v prime is not equal to v. Right? So basically that means that if you put your molecule in a specific vibrational state, it stays in there. It doesn't talk to any of the other ones. So It doesn't, no molecule will simultaneously, by itself, exist in two states at once. It can only exist in one. And that's what that means. Basically, if your molecule is in the V state, there's no probability of finding it in the V prime state. That's all it's saying. All right, that's the same thing for the hydrogen atom. All the other wave functions we've ever looked like are like that. But it's worthwhile to remind you of that. We're going to see where that breaks down. That actually breaks down eventually. And there's a probability, well, it sort of breaks down. And we'll talk a little bit about how that works. The selection rules, which are the allowed transitions, spectroscopic transitions. How can we take a molecule, say in the ground state, what states are we allowed to promote it to, are very simple. And that's that delta V is either plus or minus 1. All right, so in order to excite a molecule vibrationally, we can't go plus or minus 2, plus or minus 3. You always have to go one rung up the ladder of energy. Right? You can't go up 2 rungs. You can only go up 1. This actually does break down, only valid for harmonic oscillators, perfectly harmonic ones. Right? It actually does break down, but in general, the V prime equals plus or minus 1 transitions are the strongest ones. If you've done the SO2 lab, or when you do it in PChem lab, you'll see a bunch of really strong transitions for SO3, SO2, and I think there are 3 of them. And then there's a 4th one that's listed that's called an overtone, which is delta V equals 2. And that's technically a forbidden transition, but it's allowed. It happens that you could go from V equals 0 to V equals 2 because the molecule's not harmonic. All right, we'll talk about how that breaks down when we loosen our harmonic approximation. We'll talk a little bit about how that works. Just as a reminder, I just wanted to say that I'm going to just label these just so I keep track of them. That harmonic oscillators, perfectly harmonic oscillators, do not disassociate. Right? So no matter how much energy you put into that bond, it always stays a bond. It doesn't break apart. Right? That's obviously not physical. Right? So we know that eventually this model for vibrations breaks down, because if you vibrate and you stretch a bond enough, it's going to fall apart. So we know that breaks down somewhere. Just the question is where. The selection rules are plus or minus 1. It's really easy to prove that. I won't prove it here, but basically it's always plus or minus 1. Easy math. I might put it on the homework. Yeah, so this is it. This is a harmonic oscillator. Vibrations are really simple. Of course, the diatomic molecule only has one vibration, the stretch of the bond. Many molecules have many more vibrational modes, right? SO2 has 3, and I'll explain the rules for that today. But this is it. This is all harmonic oscillators tell us. There's a equal, right? The spacings between all the energy levels are equally spaced. You can only move by one at a time. When you shine light at your molecule, you can only go by one. And they have these oscillatory wave functions. And they have, and just as one more thing, the energy, just to remind you, the energy, h bar omega v plus 1/2, where omega is the square root of the force constant, the stiffness of the bond K, divided by the reduced mass of the molecule. Okay, that's it. That's all a harmonic oscillator is. We can calculate more interesting things about the harmonic oscillator, but the essence of it is these simple rules. V plus 1/2, equally spaced energy levels. You can only move between them plus or minus 1. And they're all orthogonal. They don't talk to each other. Let me mute my phone. I apologize. Instagram blowing up. Now, what I want to talk about a little bit is an interesting property of harmonic oscillators. So again, or quantum springs, if you will. A very unique property. And I want to explain, I didn't bring my slinky, unfortunately, but it would be useful to have it for this expression. So what I want to do is a small experiment with a regular slinky. So again, a slinky has the same potential effectively as a harmonic oscillator. It's a spring and it vibrates and does everything we know and love. So let's imagine, I'm just going to draw my potential really quick here. Right? So energy displacement versus energy here. Here's my harmonic oscillator potential. This is L0. Okay, and I want to stretch it some amount. All right, I want to put some energy into my system. All right, and stretch it a certain amount. Right, so let's say I stretch it to here. Right, remember, this is stretch and this is compress. So what happens when I stretch it and I let it go? Well, the system's going to oscillate. It's going to return back, and then if there's no loss of energy, it's going to compress all the way up to the same point on the opposite side of the potential. So let me just bisect this so you can see that. So this is my first step, and I release it, it ends up here. And if there's no loss of energy, the spring's going to oscillate between this maximum point of stretching to this minimum point of stretching. Because of conservation of energy, they're going to be at the same potential energy of each other, right? So it's going to be a straight line across. Okay, so what that means is that no matter what I do, if I put this much energy into my system, we'll call it E, that my spring's never going to stretch past this point or compress past this point, right? So we call these points turning points. Right? And it's literally where the spring turns around and goes the opposite direction. Right? It's the maximum displacement either in the compression zone or in the expansion zone. Right? So these are the turning points of the curve. Which means that again, with this energy that you're never going to see the spring be up here, right, and really, really further stretch because there's not enough energy for it. Right? So that the spring's only going to sample all the points of length between these two turning points. Okay? Now the question I'm going to ask is that also true for quantum mechanical springs? Does a quantum mechanical spring at a given energy go past the turning points? Is there a probability that it can be longer or shorter than classically what you would expect from the energy? And in fact, the answer is yes. And I want to show that to you today. And by describing the math of this just a little bit. So what I'm going to do is this. I'm going to redraw my potential one more time, just a part of it. And I'm going to draw just the ground state of the function, the ground state wave function, d equals 0. This is again an energy 1/2 h bar omega. Remember, that's already something different than a classical spring. If I don't put any energy into my spring, then the only length it can be at is L0. It can only sit at the bottom of this potential. But if I don't put any energy into my quantum spring, it always has some residual energy. It's always vibrating, right? So there's already a huge difference between the two. But it gets weirder. And the thing is that the wave function for the ground state, I won't write it completely out, but it's proportional to minus e to the x squared over 2. Right? I've gotten rid of the constants and stuff. But this function extends to infinity. Right? The only where it's 0 is where x is infinite. So if I were to draw this, let me extend my horizontal line here so it's a little more obvious. Outside of the potential, psi squared, right, remember, is the probability. The square of e to the x squared is just e to the x squared, so it doesn't really change the functional form. It goes to 0. Let me see if I can draw this right. So here's my peak. It goes to 0 as x goes to minus infinity or infinity, but it doesn't go quite to 0. So if we were to integrate this, there's a little bit of area under the curve outside of the turning points. Again, the turning points are right here. Right? So if this were a classical spring, the furthest it could ever extend are at these points. Right? But there is a little region out there, like so, where the probability is non-zero. Right? So remember, in the particle in the box, the particle can never leave the box, right? The potential is infinite. But here we have a finite potential, right? And so therefore, it turns out that there's a little probability that the molecule can, what we call, tunnel out of the potential. It can exist in a state that is beyond what you would predict classically from the energy, right? This is what we call the quantum tunneling region, if you will. or the forbidden region, right? It's forbidden because it's past the turning point. But there's a probability that the bond can be longer or shorter than you would predict for its energy. Right? And we can prove that very easily. All we need to do is integrate this wave function in these regions right here. Right? So all I need to know is the x value for these. What's the x values for these turning points? And then I can integrate from that point out to infinity and multiply it by 2 because it's symmetric. Well, I only have to integrate one side and multiply it by 2, and I can get the answer. All right, so I want to work through that integral today. All right, it's not too hard. So, the probability again, so let's call this point here the turning point. Let's call it xt. Okay, and so this is minus xt. So the probability the bond is outside the potential, the classically allowed region, is going to be equal to 2 times the integral from xt to infinity of psi squared dx. Right? Remember that the integral of psi squared gives us the probability of finding something in a certain region, and the region we want to calculate is the region bounded by xt out to infinity. Right? I don't include the other side because, again, it's symmetric around the origin here, right in the middle, so this area is the same as this one, which is why I multiply by 2. So all we need to do is determine what x sub t is in terms of the energy. Right? What is that actual value? Let me grab my eraser. dx. Okay, so we know that the potential energy at that position is equal to 1/2 k xt squared. So that means that xt is equal to plus or minus the square root of 2 times the potential at that energy divided by E sub f. Or sorry, that's not a number. Divided by k. Sorry. But what is V? What is the potential energy at that point? Well, it's just the energy of the ground state, which is 1/2 h bar omega. That's all it is. Because we have things in terms of k here, I'm gonna write this as 1/2. So v of x sub t is 1/2 h bar times the square root of k over mu. Okay. And so we just have to plug this in. So if xt is this, the answer to this then is that xt is equal to plus or minus 2 times nu plus 1/2, where nu is 0 in this case, h bar omega, divided by k. So that's equal to plus or minus 2v plus 1/2 h bar times the square root of k over mu divided by k. And we got a lot of radicals and stuff here. And so on and so forth. So this ends up being, if you let alpha equals h bar squared over mu k to the 1/4 power, then xt is equal to plus or minus, so for v equals 0, it's going to be h bar omega over alpha squared k. Anyway, so it doesn't matter. You get some number here. But it turns out that this number is completely irrelevant because once we do U substitution, it'll go away. So the probability now is 2 times the integral from xt to infinity of our wave function, which is going to be, I don't have the full thing here, but it's proportional to alpha. Let me get the actual value. I apologize. Let me just get it right. I always forget the coefficient on the outside. Yeah, thank you. So it's alpha over pi to the 1/4. See, v is 0, so that's 1. E to the minus alpha over x squared over 2, and this is all squared. Dx. Where alpha is this reduced term here. It's just a variable. It's not super important. It just tells you the width of the potential, how shallow or how steep it is. And so once we evaluate this out, this ends up being 2 over alpha over pi to the 1/2 integral of from infinity to xt of e to the minus alpha x squared. Because the 2's cancel out here, dx. So we have this integral of e to the minus x squared that we have to evaluate. And you can do this integral numerically. You can also do it, it has an exact solution. But anyway, you could plug this right into, if you let, for instance, where did that other piece of paper go that I had? Sorry, I have the wrong one. This is equal to 1 over pi 1/2. I'm doing U substitution here. From the integral from 1 to infinity of e to the x squared dx. Right? So I did some U substitution, and all the alphas go away, and you're just left with a factor of pi and this integral from 1 to infinity of e to the minus x squared dx. Right? So once you do U substitution. So this is a really easy integral. You can just type it right in. You can just type it right into Wolfram alpha to evaluate it. And what you find is that this is, I need a factor of 2 here because I forgot the factor of 2. This is 2 times 0.0786. So that means that the probability that the bond is past the turning points is on the order of about 16% of the time. That's a significant amount. So that means every time we take a measurement of our bond length, take a picture of it, 16% of the time it's going to be in this region that a normal spring would never exist in. Right? And this has really super important consequences, is that if you imagine that you have a bond that is very floppy, and you have light masses associated attached to it. Say, for instance, a very weak hydrogen bond, something with a hydrogen that's very labile, like a Lewis acid or a Bronsted acid, a hydrogen that just falls off. And there are many reactions and many things that happen in chemistry where you have kinetics that occur, reactions that occur where this hydrogen gets transferred, but the activation energy of that reaction is so high that at the temperature you do it, it doesn't happen. However, despite the fact that that's the case, that thermodynamically this reaction shouldn't go forward or it should be very slow, the hydrogen is oscillating enough and exists outside of these regions of the potential so much that it can actually extend into a region where it can be picked up by your other reactant molecule. Right? So without even providing it the sufficient amount of energy to disassociate, right, which would mean to get over this big hump to disassociate the atom, effectively what the hydrogen atom does is teleport. Right? It's attached here, and then there's a probability that while this bond here, this initial bond that's attached to is vibrating, that the hydrogen extends far enough into outside of the potential of its bond that it falls into the potential of another bond. And then that atom, now that hydrogen is attached to that other bond. An example would be like this. Imagine we have this reaction like this that has a large activation energy. So delta E sub A is much greater than KT. All right, so the activation energy is much larger than the available thermal energy. And so we could draw this in a very simple way with potentials. Get rid of this math here because it's not super important. So let's imagine that our potential for our molecule AB, AH, is in black here. This is the bond, the AH bond. And let's say that this is a reaction coordinate. And somewhere and at a slight distance is that B molecule that wants to associate with BH. Or maybe this is BH here. Right? And AH, right? And the molecule, the system is localized initially in AH, right? So our system, let's say, starts here. Right? I'm going to make this a little floppier, actually. What I'm going to do is I'm going to make this a really wide potential, something like this. Yeah, let's just do that. That looks good. And so let's say that our AH is in the ground state, so it's sitting right here. Right? And then there are some potentials, there's some energy levels over here as well. Maybe something like that. Okay. So our molecule is localized in this V equals 0 state, right? So the hydrogen, the wave function of that hydrogen bond, the AH bond, it looks like that. But because the wave function exists outside of the bounds, if we extend this out, there's going to be some region of the hydrogen of the wave function of the hydrogen that exists within the potential of where it can attract the BH to be, right? And so even though in order for thermodynamics for this to occur, what would have to happen is you would have to take this bond and excite it super high, and then cross over here, and then relax down, right? This is thermodynamics, right? Thermodynamics says that you have to get the system high enough energy to cross the barrier, and then have it lose its energy to stabilize in the product. But we can circumvent that entirely by realizing that the hydrogen might have some probability of it actually exists within the space of the BH bond, or what would exist in the BH bond, the potential of B with respect to H. And so instead of going over the barrier and then localizing into the product well, this is the products, it instead teleports through the walls. Instead it just goes straight through. Right? And this is called tunneling. Right? And I've probably mentioned this term before when we've looked at it, but this is the big event of this. And there are lots of reactions that do this. There are, for instance, reactions like, imagine this, for instance. Here's a really classic example of this type of hydrogen bond tunneling. And this comes from some research that I've done in the past. So if you take, and I've mentioned this reaction before, if you take vinyl cyanide or acrylonitrile, there's multiple ways to break it apart, but I want to focus on two in particular. One is a reaction that has a transition state that looks like a triple bond forming with a CN group plus H2 to then form cyanoacetylene and H2, or sorry, actually it's two H's, two H radicals that then recombine. that. So that's one way that it can react. Another way it can react, this is on a separate scale, and fall apart, is the loss of H2 together across the bond like this. This is the transition state. And this is very, very exothermic. Okay, so what's happening here is that one hydrogen gets plucked off, then another one gets plucked off, and then they recombine later. And here the H2 forms immediately by homolytically cleaving to form cyanoacetylene. These two reactions are in competition with each other. And the activation energy for this, for both of these, are huge. All right, so in order to actually get them over the barrier, the amount of wavelength, you actually have to shine UV light at this. The wavelength equivalent of energy is about 190 nanometers. This is about 300 kilojoules per mole, roughly. Okay, so big barrier. Right, so at 300 Kelvin, at room temperature, acrylonitrile is never going to break down into cyanoacetylene. Actually, it's even lower than this. It's about 100 nanometers. It's about 100 nanometers, sorry. So it's about 100 nanometers. So what we do in order to see this mechanism is we have to pump our vinyl cyanide with a ton of energy, okay? And so we do that. So I did this, and I see both products. I see hints that both of these mechanisms occur. But the interesting thing is that, and I can't show this, is that this might, if this is 300 kilojoules per mole, this one's about 250. It's got a smaller barrier. So it's very exothermic. And it has a lower barrier than this one, which is endothermic, and it has a bigger barrier. All right, so you would think, okay, this reaction doesn't occur hardly at all. This one's going to occur. It's exothermic and has a lower barrier. It's going to be faster and more thermodynamically accessible. And so what we did is, so let's say this gap here is, you have to have 100 nanometers of energy, of light energy, to get over this barrier. So what we did was, instead, you can't really get a laser at 100 nanometers. It's pretty tough. But you can get one at 193. So what I did is I took a 193 nanometer laser, which gets me somewhere like right here. Right, and over here, it actually puts me above the potential, 193 nanometers. So by shining 193 nanometer light, this is ultraviolet light, UV light, very bright UV light, not visible. That's enough energy to get this over the barrier. The super exothermic reaction, the one that the system prefers, enough energy to get over the barrier, and we see thermodynamic results here. Right? We get over the barrier, you have kinetics, you form your products, they have a lot of extra energy because they gain a lot of energy. So the products are hot due to exothermicity. They gain a lot of energy as they form. And kinetics are fast. Right, this reaction occurs on the order of one molecule reacting every nanosecond or so. It's pretty quick. But here's the problem, is I want to see a competition between these two mechanisms, but when I shine my laser at my molecule, I get over the barrier in this case, so I would expect this to happen, of course. Everything is working great for this main reaction. But in this upper reaction, I still don't have enough energy to get over the barrier. So even when I include the added thermal energy at 300 Kelvin, this whole thing's at 300 Kelvin, Just assume everything's adapted for having that extra 300 degrees of energy, KT. I still don't have enough energy to get over. But what would I expect if they could get over? Right? What if I start to see products from this? Well, first they would be formed slowly, right? Because I still don't have enough energy to go over the barrier. Very slowly. Maybe somewhere on the order of 10 to the 4 to 10 to the 5, 6 times slower than the other. Right? A million times slower. And they should be cold products because they don't gain a lot of energy because it's exothermic, right? The molecules have to lose energy to get over the barrier compared to the starting point. But in the other reaction, they actually gain energy, right? Exothermic, this is endothermic. So what I would expect is to see very slowly formed products that are cold. Actually that are hot because you need a lot of energy to get over this barrier. Sorry. So they're also hot, but they form very slowly. Right? They're hot because you have to have a lot of energy to get over this barrier, and they don't lose a lot of that heat to get over it. So they're going to be fairly hot at the end. So here you get fast kinetics, hot products. And here thermodynamically, you would expect to have very slow formation of product kinetically, and they're still hot. Now what happens is interesting. What I see is, one, I see a fast formation, majority formation of hot products. So let's call this mechanism 1 and this mechanism 2. All right, I can show that they're hot. They actually come out rotating very quickly. They have an effective rotational temperature of about 1,000 Kelvin. They're rotating like crazy. They're super hot. And they're forming so fast I can barely even keep track of the kinetics. Right? It's like a light switch. They're not there and then they're suddenly there. But I also see something else. I see a slow, or I see an intermediate speed formation of very cold products. It's about 100 times slower than mechanism 1, not 10 to the 6. And the temperature is effectively about 200 Kelvin, which is less than room temperature, the temperature I did the experiment at. So these molecules are not hot, they're actually losing energy as they go over the barrier. The reaction process makes them colder, because in order to get over some barrier, or whatever they're doing, they have to lose energy somehow. And so they end up losing quite a bit. And so they show up, so here the temperature is on the order of about 1,500 Kelvin. And here, and you see some cold products at 200 Kelvin. Well, I just predicted that the only two ways you can form this is either through a really, really slow one that goes 1,000,000 times slower than the main one. They both form hot products. So it must mean something else is going on. And I do one more observation. I replace hydrogen by deuterium. So the mass of the atom that's leaving doubles. Right? So that means that omega, H bar omega, goes to about roughly half of H bar omega for the original one. Right? So deuterium, it vibrates more slowly because it's heavier. Remember, omega is K over mu, so mu gets bigger, so the vibrational frequency decreases. And what I see is that the reaction slows down with deuterium by almost 1,000 times. So by replacing a hydrogen with deuterium, I can basically kill the secondary reaction that occurs. Thermodynamically, it shouldn't matter. Deuterium and hydrogen have effectively the same electronic properties. Right? This is an electronic direction. Right? You're manipulating electrons to move from one structure to another. It shouldn't matter if I change a deuterium or to a hydrogen, because it's changing one AMU to two AMU. It's not really a big change. But in terms of vibrations, it's a big change, because you have an atom that's at the end of your spring that is mass 1, and then you're adding a mass of twice that. So it's actually a large fractional change vibrationally. But the interesting thing is that it slows reactions down by 1,000 times. Right? If this were occurring thermodynamically, that would not happen. It would maybe change by 1%. So H to D thermodynamically leads to the rate, this is the rate of the hydrogen over the rate of the deuterium to be about 1. Sometimes it's a little higher. Let's say it's about 1.1 or something like that. That's typically what people see. But if the reaction is not occurring thermodynamically, as in it's going over the barrier like you would expect, so quantum mechanically, if the hydrogen tunnels through its barrier, this rate ratio can be anything. It can be over 100. It can be anything, really. And the reason why this is, and so what we determined then is that this reaction occurs not because it's going over the barrier. It doesn't have enough energy to go over the barrier. But instead what this molecule is doing is going directly through the barrier. It's tunneling. Right? Because if you think about it, if we think about the wave function of the molecule at this level, it probably oscillates a lot because it's at a high vibrational state. But there's a little bit of area under the curve. Right? That hydrogen can exist at a position that exists within this barrier. And in order for it to do anything, it can either, right, you're never going to observe it in the middle of the barrier. You can only observe it on the inside or the outside. So this is not a real area, if you will. So it literally is going to come from here. It's on this side, and there's some probability, it's small, but there's some probability that it just shows up over here. And then what happens when it's over here? Well, there's only one option. It just relaxes down to the products. Right, so tunneling, and there are so many examples of this in biochemistry, surface science, astrochemistry, organic chemistry, where you see this. And in fact, the term of this study where you replace a hydrogen with a deuterium to see how the rates change is what's called the kinetic isotope effect. Right, and if Kh over Kd is around 1, tunneling is rare, but if Kh over Kd is much greater than 1, then tunneling dominates. Right? And there are lots of reactions where that shouldn't occur, but do, because tunneling, there's some probability of tunneling. All right? And I just want to explain just very briefly why deuterium is slower. So again, here's my potential again. And let's imagine that the ground state of AH is right here. 1/2 times H bar times delta square root of K over mu. All right, so there's AH bar. There's my wave function. It's not really the best wave function in the world, but bear with me. All right, and then now what happens when we replace H with D? Well, when H goes to D, mu decreases or increases, right? Because now the mass of the bond, if you will, the masses on the ends of the bond are larger, so mu increases, which means that, and K is roughly constant, because there's nothing really different between, right, the mass changes for isotopes, but the properties of atoms don't really change amongst isotopes if they're all stable, so the stiffness of the bond is still the same because the deuterium is not really different than hydrogen electronically, but the mass gets bigger. So that means then that this number gets smaller, And so for AD, the ground state energy is slightly lower. And because it's heavier, it doesn't oscillate nearly as much. It's a heavier mass on it, so it doesn't wobble like as much as the hydrogen does. So the wave function also is slightly narrower. There's less, so deuterium has less internal energy. Right? The 0 point energy is lower because it's heavier. And the wave function narrows. Wave function narrows because an AD bond has less amplitude than an AH bond. Right? So it oscillates, it moves around less, and it's also at lower energy. So because it's at lower energy, that means that the energy of the deuterium complex is down here instead, so it's even further away from the barrier. But also because it has less wobbly and less floppy amplitude, that means that the area under the curve outside of the potential where it tunnels, the tunneling region, is also is a bit smaller. So deuterium in general is going to tunnel more slowly than hydrogen. And so if you have a reaction that's dominated by the system tunneling or literally teleporting from the reactant to the product side, then deuterium will play a big role in slowing those reactions down. Right? People do these kinds of mechanisms all the time in all fields of chemistry. Right? This is not just a P-Chem kind of esoteric concept, but anyone who ever studies mechanisms or kinetics at any level of chemistry often does kinetic isotope effects, because if you want to distinguish between thermodynamic and quantum mechanical tunneling mechanisms, this is the tool that we use. Right? That deuterium is heavier, it's less wobbly, it's less floppy, it tunnels less, it's heavier, therefore it tunnels more slowly than hydrogen, so you can kill tunneling by replacing an atom with a heavier atom. Right? And this is all due to the fact that harmonic oscillators always have some residual energy in them, right? They're always vibrating, no matter what energy they're at. And they can vibrate outside of the bounds of their potential, right? So they can cross through barriers. They can cross through space without having to to overcome a thermodynamic impetus or overcome a barrier. So it's a really unique property of harmonic oscillators. We'll look at more of this as we go through this class. Any questions about that? Okay. All right, so we got about 20 minutes left. I want to talk just briefly about, and that marker's basically dead. I'm just going to throw it over there. There we go. We're talking about the validity of the harmonic oscillator approximation, right? I've already kind of hinted that it doesn't always work, right? There's a limit. If we get the high energy, eventually the bond has to break. And the question is where does that occur? All right, and what we were going to find out is that the fact is 1/2 kx squared is not a reasonable model for a chemical bond. It just has to do with our choice of potential. So I'm going to introduce a new potential, more realistic potential. Maybe I've mentioned it already in this last couple semesters or so. If you remember the Leonard-Jones potential from last year, this might ring a bell. So what I'm going to do is I'm going to introduce a new model for what we call a chemical bond. For a chemical bond, instead of a harmonic oscillator, we're going to make it a little more elegant, if you will, a little more realistic. And the potential I want to use is what's called the Morse potential. And it has a kind of a complicated functional form, but it has a really nice plot. And I'll define everything. So the potential we're going to use, V of x, is this number d sub e. I'll explain what that number is in a second. 1 minus e to the minus beta. I'll again define that again in a minute. R minus RE all squared. Okay. Now let me plot this for you, and it'll be very clear why this makes a better approximation for a bond than the harmonic oscillator. What I'm going to do is I'm going to draw a potential energy surface. We'll call this R on the x-axis and V of R. Let me change this to R. I apologize. On that axis, let's define our equilibrium bond distance. I'll put it right here. And so let's think about a little bit about how this function acts as we go from R equals 0 to R equals infinity. So we can draw this. So let's do R equals 0. If R is equal to 0, then this term is big. You have hold on a second. Yeah, it's big, right? So you have e to the minus beta times the negative number. So that's e to a positive number. 1 minus e to the positive number is a big negative number. Squared, it's an even bigger positive number. All right, so as R goes to 0, V of R explodes positively. All right, so as R goes, then the next limit is where R equals RE. Well, if R is equal to RE, then this is 0. All right, so you have e to the 0, which is 1. 1 minus 1 is 0. So the potential at R sub E is 0. And then as R goes to infinity, you have a big positive number here. So e to a negative big number is 0. 1 minus 0 is 1. 1 squared is 1. So it's dE. So as V of RE goes to this value d sub E. All right, it has an asymptote. Okay, so that means then that this goes to infinity. It goes to 0 here at R sub E. It goes to some asymptote d sub E. At infinity, I'll draw it right there. There's d sub E. And it basically explodes as you go to R equals 0. So like that. And then it starts to approach this asymptotic limit as the bond length gets longer and longer. Something like that. Okay. So let's interpret some values here. Well, we have two constants. Well, R sub E, which is the bond length. Right? It's pretty easy. It's got units of angstroms. D sub E has units of energy, right? Because V is proportional to D sub E. V is an energy, so D sub E is an energy. And D sub E is just the distance between the bottom of the potential and the asymptote. And D sub E we call the dissociation energy. Right? It's how much energy you need to put into the bond to break it. Simple as that. Right? If the molecule is here at the bottom in its equilibrium position, you've got to pump it with this much energy in order to get it to maximum separation. Right? All right, and then beta. Beta is just the width of the potential. So beta is inverse of the width of the potential. So kind of the width here is proportional to 1 over beta. So the bigger beta is, the more sharp the potential is, how much more narrow it is, right? As you might imagine that beta has some, remember that the harmonic potential, the curvature of the potential is proportional to K, the stiffness of the bond. So beta has something to do with stiffness, how stiff the bond is, how resistant it is to stretching and compressing. So it's proportional to 1 over K, roughly. I think there's a square root in there or something like that. I think it's K1 half. But anyway, I digress. It doesn't matter. But it's proportional to the stiffness. Right? So the stiffer it is, the more narrow the potential is. Right? I'll just draw that. So large beta, your potential is going to be very, very sharp, like this. And small beta, your potential is going to be broad, like that. Right? There are different types of bonds, different types of stiffness. Right? This is going to be like kind of like an XH bond, right? Something that's really kind of floppy, where X is whatever. And this is like a carbon-carbon double bond, right? Stiff, hard to break. Again, we have to represent how floppy a bond is. Now, how does this apply to the harmonic oscillator approximation, right? Why are we even using this? And the reason why is that this is a correction to the harmonic oscillator. Let me draw it one more time. Again, there's a lot of potential plotting here. So, sorry for your paper. But let's draw a potential, a Morse potential. Maybe it looks like this. I'm going to label it, first be there. What you can show at displacements r close to r sub e, so if you look in kind of the region here, if you will, the Morse oscillator, the Morse potential is very, very close to 1/2 kx squared. Right? So if I were to draw a parabola here where the parabola is centered here, it agrees. And then as the energy starts to increase, it starts to disagree completely with the Morse potential. So if I were to go ahead and to draw my energy levels inside this potential, my harmonic oscillator potential energies. Oh my God, these pens are dying. So let's put maybe 1/2 h bar omega here, v equals 0. Or maybe let's make it a little lower, sorry. V equals 0 here. All right, we can see that in this region here, around the potential, around V equals 0, the harmonic oscillator and the Morse potential look almost exactly the same, right? They almost agree perfectly. And the reason why they don't agree perfectly there is because I can't draw properly. But at V equals 0, or near V equals 0 energy, which is 1/2 h bar omega, the Morse potential, which I'll write V Morse, is effectively the same as the harmonic oscillator potential. Right? And so if you think about it, as the potential, as we start to get higher and higher energy, I'll draw my harmonic oscillator levels like this. We get higher and higher energy, you can see that the potential starts to disagree even more with the harmonic oscillator approximation, right? The closer I get to disassociation, the bigger the disagreement is. So what happens to the energy levels when we go to the Morse potential? They no longer become equally spaced. So in the Morse potential, the energy of the V equals 0 state, I'll write that for Morse, is equal to the energy of the V equals 0 state for the harmonic oscillator. They agree perfectly, in fact. And then as V is greater than 0, the energy of the Morse potential of that state ends up being less than the one for the harmonic oscillator. And the difference gets larger and larger as V increases. So if I were to draw the levels in purple for the Morse oscillator, the V equals 0 is exactly there. And then the one for V equals 1 is slightly lower. And then for V equals 2, it's even more slightly lower. And for V equals 3, it might be completely off. Right? And in fact, as we start to get higher and higher, the spacings get smaller and smaller. They're no longer equally spaced. So as we start to approach the limit, the energy level spacings in the Morse oscillator get smaller and smaller and smaller. Eventually, as we start to get to the disassociation limit, they're really stacked on top of each other like this, right? They're no longer equally spaced. So on and so forth. So in the Morse potential, and let me have I have the right formula for it here, right here. Let me write this in a big text. So a more proper way to measure the energies, proper formula for energies, from the Morse potential is that the energy, as a function of V, has this h bar omega V plus 1/2 term, just like the harmonic oscillator. And there's a new term we'll call x sub e V plus 1/2 squared. So there's a squared term now. And this term we call, this x sub e, is what's called the anharmonicity constant. So it tells you how anharmonic the potential is, how far it deviates from the harmonic limit as V increases, right? The more this starts to bow out, the more anharmonic the potential we say is, right? The less harmonic it looks, right? And remember, all harmonic means is that the energy levels or the notes of the spring are equally spaced. So an anharmonic spring is one where the energy levels are no longer spaced. In fact, I can show you experimental evidence of this. So if we look at the data for HCl, for 1 hydrogen 35 Cl, and we look at the vibrational states, so we'll write transition, and then the harmonic oscillator prediction for the frequency, and then the Morse potential. I'll just call it Morse. And then experiment. Right, so we're going to make two predictions, one with the Morse potential, one with the harmonic oscillator, and one for the experiment. So the first one is the ground state to the first excited state, variable 1. This is predicted the harmonic oscillator to be 2885.9. These are in wave numbers. Yeah, the Morse potential, again, remember the Morse potential energy for the V equals 0 is the same, so you get the same prediction. And the experiment agrees perfectly. Okay, great. So if you were only to look at the V equals 0 to 1 transition, the fundamental vibrational transition of HCl, you would see that, well, obviously it's a harmonic oscillator. Everything agrees perfectly. Of course, not surprisingly, it starts to break down. So if we look at the energy difference between the 0 and the second state, right, so I'm just skipping 2 instead of going one by one. It just makes this easier to kind of look at how the energy levels change by doing it this way. We would predict the harmonic oscillator that this is at 5771.8. It's at twice this. Right? All this is twice this number, right? They're equally spaced, so it's double. The Morse potential shows that it's quite a bit smaller, right? Because HCl is anharmonic, it has a disassociation limit, and that brings the V equals 2 state a little lower in energy from the harmonic prediction. And guess what? Experiment agrees. Experiment agrees almost perfectly with the Morse prediction. It's off by 0.2 wave numbers. Okay, so maybe it's not anharmonic. Or maybe it's not a harmonic oscillator. And so we can go to the third state. This is at 8657.7. The Morse oscillator shows that you're off by almost 10%, 8347.5. And experiment agrees, but it doesn't quite agree as much as it did for 0 equals 2. So the Morse oscillator is already starting to disagree a little bit, and that disagreement gets worse and worse and worse. Right? But still, it's much better than the harmonic oscillator prediction. Right? The harmonic oscillator prediction is off by almost 300 wave numbers, which is 5%, roughly 5% error. And this one's off by half a wave number, right? And 2-3 orders of magnitude better prediction. Right, so in general, molecules are not harmonic. Okay, when we get to spectroscopy, we'll return to this concept a little bit, and we'll talk about this. Right, how do we measure, how do we model the energies of the vibrational states of a molecule with good accuracy? And it turns out that the way that we do it, just as a hint, or just kind of as a spoiler, is that we add a term that's cubic in V, and then one that's quartic in V, and one that's quintic in V. Right? We just add additional terms, make the polynomial bigger and bigger, and that gives us better and better answers. Right? So the solution to making this better is to just make a bigger function to fit. And it turns out that that is actually, that sounds like a cop-out. Right? Why? You know, if this doesn't work, well, let's do the classic thing and add another parameter, v plus 1/2 cubed plus d, v plus 1/2 to the fourth. I mean, why wouldn't we do that, right? You would think that that's not physical, right? That we're just making something up. But in fact, the Morse oscillator is built around the concept that improved predictions to the energies only require you to add an additional power to the expansion in v plus 1/2. And that actually is born out of the mathematics of the harmonic oscillator and the anharmonic oscillator. That's cooked into the theory. So even though this seems like a cop-out, well, if my model doesn't fit to a parabola, let's fit it to a cubic. If that doesn't work, let's do a quartic. But in fact, that's exactly how this model works, right? So it's really powerful for this. So the idea is that better and better approximations correlate to higher order polynomials. Right? And that's a physical consequence of the Morse potential. Right? The Morse potential is built around the idea of taking a harmonic oscillator and perturbing it and distorting it in a polynomial way, right? To add this polynomial correction to the energy. And that gives us a really easy formula to use to calculate vibrational structures and vibrational energies and vibrational spectroscopy, doing infrared, in order to do increasingly more precise fits and to think about the energy of the molecule at really, really close to the dissociation limit, right? Up here, you're very anharmonic. So the quadratic part and the linear part is not going to be very accurate. You need the higher order terms up here. But the model is built around those higher order terms are the things that become important, right, physically. So this gives us a really, really simple model. That's really quite possibly the simplest model you can think of to correct for these anharmonisms, these things that pull us out of the harmonic limit. Right, and it really leads to a lot, and I don't really quite have the time to really explore it yet, and so we'll do it on Monday. I just want to give you an example of what this looks like. So again, if we had a harmonic oscillator, we have equally spaced levels, But if our molecule looks like a real molecule, again, its potential looks like this. And the levels are roughly equally spaced. And then they start to get closer and closer together. Right, so if we compare these two things on the same scale, right, these have the same scale. Right, this harmonic oscillator prediction predicts that we only have 4 or 5 energy levels within this energy limit. But due to anharmonicity, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 levels anharmonic, right? So there are 10 levels here, and there's only 5 here. Right? So causing a potential or treating the bond as anharmonic really changes its properties. But the point is that this is not a good approximation, right? So again, the fact that this is h bar omega is okay, but the fact that this predicts as h bar omega is bad, because this is roughly h bar omega. But obviously, this gap right here is not h bar omega; it's much smaller, right? And the gap, the way that the gap closes, gap between levels closes as x sub v, it turns out v plus 1/2. So that the deviation from linearity, or the deviation from equal space, increases as a linear function of v. So if v equals 0, it basically, negative v plus 1/2. So at v equals 0, the spacing is exactly what you would expect it to be. And then, no, it's actually x sub v. I apologize. But as v gets bigger, the gap actually gets smaller and smaller and smaller. And it's proportional to how anharmonic the system is. How bowed out it is at long distance here. Okay. We'll explore this later. More. So when we get to vibrational spectroscopy, we're going to have a question is, well, what else does this break? Right? Already it tells us that our energy level predictions are going to be off by some polynomial order, or square, or a cubic. Off by a little bit. But the question is, do other things start to break? And it turns out that not only do the energy levels start to break, but you start to have other effects as well, too. For instance, the selection rules. So remember that delta V here can only be plus or minus 1, right? You can only go up one rung at a time in a harmonic oscillator. But in the Morse oscillator, delta V can be 1, it can be 2, it can be 3, and so on and so forth. And they become increasingly rare as delta V increases. So for instance, you can actually have the 0 to 2 transition in a real molecule. In the Morse oscillator, if you treat it as an anharmonic potential, it actually makes that allowed. And you'll see that in the SO2 lab when you go to analyze that spectrum. Again, there are 3 vibrational modes, 3 harmonic vibrational modes, and there's an additional band at around 2,500 wave numbers that isn't associated, that's associated with the molecule, but isn't one of those main modes. And what it is, in fact, is an excitation from 0 to 2. And an excitation from 0 to 2, which is forbidden by the harmonic oscillator. But because the molecule is anharmonic, that transition appears. It's very weak. It's just above the noise. So you can barely see it in your spectrum, but it's there. And the reason why it's so weak is because it's only tiny little bit allowed. Right? Just the molecule is just anharmonic enough. It's just bowed out enough that it allows it to be no longer forbidden and allows it to be a possible transition. So in real molecules, you don't just expect to see a bunch of 0 to 1 transitions for all your lines and that's it. But in fact, you see lots of lines associated with these things that break down at the anharmonic limit. All right, we'll look at those more carefully as we get to spectroscopy. Okay, that's all I have for you today. Let me get my exams out for you. Make sure to sign the front. It's due back in class unless we've approved otherwise. Thank you. I have it in reverse order. Victoria. sure to sign it. Again, you're allowed to use anything online, in your notes, in your book. You just can't use each other. Which I'm not sure is, yeah, I'm going to say it totally is enforceable. Good luck, everybody.
We email you a second serve online resource.
I'm sorry?
So we email you a second serve online resource.
Yeah, I'm happy to take questions. The worst thing you'll get from me is a no. I won't do anything other than tell you no, I'm not going to help you with that.
Thank you.
Thank you.
Have a good weekend.
Hey, you too, thank you. Thank you. Have a lovely weekend. I'll see some of you in an hour.
Sorry.
See you on Friday, Dr. Slater.
Take care. Yeah.
For grad seminar, for our presentation, do you need to send us ahead of time, or?
The presentation?
Yeah.
No.
Okay.
No, I just need your abstract and your bio before, that's all.
Okay. See you Friday.
See you Friday.